In this slide, we will understand how to determine Cartesian vectors using angular information. So the first thing we'll do is we'll discuss a standard convention, and the standard convention is often shown in many math and physics and mechanics books. We draw a vector f in the first quadrant of the x and y axis system, and we show each of their components as if they're both positive, and we introduce an angle called theta, which is measured by convention positive counterclockwise from the positive x-axis. Now in some problems that might change, but in this case we'll define this as our standard. And also notice that in the lower left hand corner we have the I and j unit vectors as a reference. I will ask you to think about the previous lesson. Do you think that this diagram is using the scalar or vector notation for the labels? So from what you already know about trigonometry, let's think about how to apply trigonometry to understanding the components of this vector. The first thing we'll do is we'll actually draw a third line to make what is now a right-angled triangle. The f, which represents the magnitude of the vector, can now also be understood as the hypotenuse of that triangle. And so we can say the x component is the magnitude of the hypotenuse f multiplied by the cosine of theta. And if you're not quite sure where I got that, remember cosine of theta is the adjacent side divided by the hypotenuse. And this is simply inverting that equation. Okay, so here, relative to the angle theta, the fx is the adjacent side and therefore goes with cosine. Similarly, if we think about the fy component and to visualize it, we can slide it right along that third side of the triangle. The fy component is the magnitude of the hypotenuse multiplied by sine of theta. And I'll note that these relations can be applied for any value of theta as long as theta is measured positive counterclockwise from the x-axis. So for example, maybe theta is 120 degrees, and this would apply equally well to that case as it does when you see the angle as if it were an angle between 0 and 90. And we'll see an example about that later. And I'll just note in general, sign conventions are definitions to specify which way is the positive direction or sense of a certain quantity. And so by convention, the symbols fx and fy and theta are all positive in a mutual sense. But again, in some other problems, we might redefine what is positive. So here's an example. Consider the vector f written in terms of its Cartesian components. How do we do that? And so I have a vector here of magnitude 30 newtons, and we're told that that vector is angled 20 degrees, but now it's measured from the negative y-axis, okay? So how do we get the components of this vector? Well, the first method is to simply say, let's use our standard convention. And the first step to that is define the angle theta using that standard convention. It's not 20, rather it's 290 degrees, because again the convention says start at the x-axis and go all the way around to the vector, okay? And then we'll apply our formula. Fx by formula is f cosine of theta, which is 30 newtons times the cosine of 290 degrees. I'll have you verify this in your calculator, and I do recommend at the intermediate calculation level, don't round off too much. I would say take at least 4 decimal points, but if you get what I get, you should get 10.26 newtons. In a similar fashion, f sine theta is 30 newtons times sine of 290 degrees. Sine of 290 has a negative value, and we would find out that the fy component is negative 28.19 newtons. And so if I go and fill in the answers, first of all, in vector symbols, I could write completely the vector f, and notice again I'm using the vector symbol for f in the first line, is now the component fx times I plus the component fy times j, which would be 10.26 newtons times I. and then plus a negative 28.19 newtons times J. And if I label the figure, I'll put 10.26 on the X component, and I'll put positive 28.19 on the vertical component, which is really, and this is the little awkward part, that's now thinking of that blue line as in the negative Y direction, because that's how it's drawn. And so I'm going to write 28.19 to illustrate the length of that blue vector. And since the blue vector is already pointing negative, I don't double negate it because otherwise I'd have it pointing upward. So I'm going to write 28.19 and the vector points downward, so the total understood effect is negative 28.19 J. And in general, this means that if you're labeling a vector with symbols, in this case, the fx is clear, but I would label the vertical component as negative fy. And how can I see this? Because since the value of fy was negative 28.19, then the value of negative fy must be positive 28.19, and that corresponds with our convention. So in summary, if I use the scalar labeling system with actual numbers, I'm going to finally write only the magnitude of each component as long as the components are already drawn in their natural direction. So again, the vertical component is already pointing down, so I interpret that as 28.19 negative J. And as a final note, if you were to take this vector in symbolic form and you were to write fx and fy, I'm going to claim that you should not write fy, you should be writing negative fy for that component as we discussed in the previous slide. This is a bit sometimes confusing for people, so I wouldn't worry too much about it at this point, but I'm going to use this consistent notation, and the more we practice it, I think the more you'll find it's not so bad. The second method is to use direct trigonometry. We can take this vector, 30 newtons, and now let's work with the 20-degree angle, knowing that's not theta, it's some other angle. But what I can do is I can now redraw the vector components to make it look like the triangle that we've been talking about. And now I can say, from regular trigonometry, that side is fx, which is now opposite of 20. So here's where you cannot just memorize that fx is always cosine. In this case, fx would be 30 newtons times the sine of 20 degrees because it's opposite of 20, getting again the same number, 10.26 newtons. And using our strict notation, the negative fy component, which is the length of that vertical side of the triangle, is 30 newtons times the cosine of 20 degrees. And if we just do one final step, that means fy is negative 28.19 newtons, as we had before. So in summary, we get the same final answer. We see that the vector f ultimately is 10.26 newtons I minus 28.19 newtons J. And that's how we label that vector. One last comment about labeling. If I just use scalar labels, I'll write the magnitude of each component because the arrows now already tell me the directions of the components. Whereas if I use the mixed label system, I would put 10.26 newtons times I, but here I would say negative 28.19 newtons times J because now that whole expression is together the full definition of the vector. So just focus on this slide a little bit. It looks contradictory, but it's really not. The main issue is to be consistent, and in my case, I generally prefer the scalar labeling system on the left.